To do some physics, and you can use my help.
Yeah, we're trying to find what the frictional coefficient has to do with an object sliding down different inclined planes.
Well, I see you humans throwing bags at the board, and I guess you could do something with that.
Hey, you're right. Come on, let's go. Ben, you're a little close for bean bags.
My board, my rules. Huh. The bag doesn't move when I throw it on. It doesn't slide back down the board. I wonder why. I think the first thing we should do is mass it. Okay, so when we tried to mass it on my scale, we realized that the scale wasn't picking up the weight because it was so small. So instead we massed me, and I came out to 147.8 pounds. And
I'm not going to be able to land a beanbag on the board when it's tilted like this. You say your board, your rules, but you know what? This isn't fair. I mean, watch. I'm going to use physics to show you why this isn't fair. Oh, hey Ben. What do you have there?
I have Peter's phone, and I'm going to measure the angle of our beanbag, or of our bags board.
All right.
So we'll go there. So it looks like the bags board is about 9 degrees.
Now it's my turn to measure this angle. 35 degrees. From the tape measure, we can see that the length of this board is 47 inches and 1/2 inch.
And we have to do this because we have to find the velocity at the end of the bag at the end of the run so that we can calculate the kinetic friction. So to find the velocity at the end of the run, we have to calculate the time it takes for the beanbag to slide all the way down.
Wow, 1.10 seconds.
Since Ben's beanbag did not move once it hits the board, the sum of the forces in the x direction all add up to 0. This means that the frictional force is equal to mg sine theta, since those are the only two forces acting in the x direction. The frictional force is equal to the frictional coefficient, or mu, times the normal force. In this, the normal force is equal to mg cos theta, since there is no movement in the y direction. This means that mu is equal to mg sine theta, or the frictional force, over mg cos theta, which is the normal force. The mg's cancel out to make mu equal to tan theta, and then since theta is equal to 9 degrees, mu comes out to be 0.158. Now to find the frictional force in general, that is mu times the normal force, which is said before, so that is 0.158 times mg cos of 9 degrees. And then we weighed out our beanbag, and it turned out to be 0.8 pounds, which is equal to 0.363 kilograms. And using this information, we found that our frictional force is equal to 0.556 newtons. Since Peter's beanbag moved when he tossed it onto the board, we have to find the frictional coefficient for kinetic friction and the frictional force for kinetic friction. First, we have to find the acceleration in the x direction. The acceleration is equal to the velocity final in the x direction squared minus the velocity initial in the x direction squared, all over 2 times the change in x. And then for this, our velocity final is equal to 1.2 meters over 1.1 seconds, since the board was 1.2 meters and it took 1.1 seconds to go down, squared minus 0 because the beanbag started from rest when we dropped it. And then this is all over 2 times 1.2 meters, which is the length of the board. And then the acceleration in the x direction comes out to be 0.495 meters per second squared. And then the frictional coefficient, or mu, for this is equal to the force of the kinetic system over the normal force. And then this comes out to be the negative mass times the acceleration in the x direction, since that is the force acting on the system throughout the time, over the mass times gravity, since that is the normal force on the entire system as it is moving down, which is just the weight of the beanbag. The masses cancel out in this, just to make the negative acceleration in the x direction over gravity for mu. And then this is 0.495 meters per second squared, which is what we calculated the acceleration in the x direction to be, over gravity, which is 9.81 meters per second squared. The meters per second squared cancel out, and then we get a mu of 0.0505, which is our frictional coefficient. And then our regular frictional force is equal to that, 0.0505, times mg cos 35 degrees, which is our original normal force. And that comes out to be 0.147 newtons. And the reason why it's moving is because the mg sine of 35 degrees, which is our other force acting in the x direction, is equal to 2.04 newtons. And since that is greater than our frictional force, it makes sense that the beanbag would be moving in the x direction. In conclusion, this means that as the angle decreases, the frictional coefficient and frictional force increases, thus making the object less likely to move.